talk about the power series, that would be geometric. Okay? And do we have to check endpoints on geometric? No, because they always do what? Diverge. Why do we have to check endpoints on the ratio? Yeah, don't know. Okay. So again, we're going to do the geometric. And do you remember this formula? A over 1 minus R? So when I'm given that A R to the n when I started at 0, I know that this is the summation for it. Okay? So that's your power series, that's the summation. So we're still going to apply that. Okay, so first off, what makes something a power series versus series before we start? And x's. Whereas series just have how many variables? 1. Okay, so we've got both of them going on. So with the geometric, it's basically, if I have a function that looks something like this, then I can identify and say, well, that's my A. I have my 1 minus, and then this guy would be my R. So I can make this into an equivalent series. Power series, actually. And that's what we're going to be doing today. And again, we don't have to check the endpoints for geometric because they're going to diverge from that condition. We know what happens there. So let's look at our first one. It says find a power series for the function and determine the interval of convergence for this guy. Okay, well, it is set up A over 1 minus my R. So it is set up beautifully for us. So my power series that I'm going to have to go from the sum to the series, I would have to start at 0. My A was x squared, and my R was x cubed, and that's to the n. Is that okay? Is anybody confused about that step? So that's my power series. So that's the power series representing this function. And basically, if I kept writing out all these terms, if I kept going and writing out what this would be, what am I going to see this become? Okay, x squared plus x to the, let's just write it out. That would be x squared plus, plug in 0, then plug in 1, x to the 5th plus x to the 8th, dot, 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 right? It's adding 3 each time. This right here is a what? As I write all those guys out. I mean, you're seeing what the sequence is, but what's the general name that we've created? Thank you. This was the Taylor polynomial, and in this case it's actually Maclaurin, but either way, this is a Taylor polynomial centered where? Okay, so that power series is a representation of a Taylor polynomial. So basically we are saying that this function right here and this right here are going to do what? Huh? They're going to converge. Okay, so So they're going to match over a certain interval, or maybe everywhere, which we saw, or maybe just at where we are centered. Those are my three possibilities. Okay, so that's what we're seeing. So when it says determine the interval of convergence, we're saying, where does this guy match this guy over what values of x's? Okay, that's the interval of convergence. So let's do that. Okay, so my interval of convergence, I'm going to have to go and use my condition. I know that I converge when the absolute value of r here is less than 1. Yes? So in r's, we're looking for where the absolute value, what's our r? X cubed is less than 1. And recall, we're trying to get that as the absolute value of x minus c less than the radius, right? So what's bad here? Still, the cubed. So let's get our cube to go away by taking the cube root. Oh, but the cube root of 1 is still just 1, okay? So I know that that would be, and again, why do we not have to check endpoints? It's geometric. The endpoints would be in the divergence part. Okay? So if I graphed this right here, this Taylor polynomial, and I graphed that f into my calculator, where would I see them converge and look exactly the same from? Negative 1 to 1. What happens outside that radius? They're not converging, right? They're like, whoa, two different things. So maybe like from negative 1 to 1 of whatever's going on, we're matching, and then we do something else maybe. Okay? Okay. Let's look at the next one. Find a power series centered at 0 for this function. Is this in my a over 1 minus r?
No.
Not quite.
I think it would be a very simple solution.
What's a very simple solution to this?
Times everything by negative 1.
Okay. Multiply top and bottom by negative 1. Oops. So that would be negative x over minus x squared. And now I am in my a over 1 minus, we have to have r. So now we're in our setup. Say it again, x squared. You could try to do it. Okay? And what you get should be equivalent once reducing in the series, okay? So here I have my series is my a times my r to the n. And since I came from the a over 1 minus r, where do I have to start here? Since I'm using the sum part, 0. Okay, I'm going to give you one more here. Add it in a different edge here. Questions as we get started. Let's do that one. Oops. Okay, first off, I need to flip-flop the denominator just like I did on that last one. So I'm going to have that negative 1 over 7 minus 3x. Yes? Multiply top and bottom by negative 1. But this is still my issue because that's not a 1. So what can I do to everything? Divide by 7. So I can divide every term through by 7. write my geometric power series? A is negative 1/7. R is 3x over 7. Bless you. Good? Okay, so questions about what we just did? And if we wanted to find an interval of convergence, could we? Yes. Okay, these are just some operations. If you want to kind of look through them, it's just basic behavior, kind of like polynomials would work, okay? So they're very intuitive, and again, if you want to look over them, wonderful. Okay, so this last example I think is a lot of fun. Kids are like, what? Find a power series for arctan. Arctan doesn't look like that f of x into a rational expression to try to manipulate it. What? Right? Okay. But there's something related to arctan that does. Sam? It is the derivative. Okay, so I know that, hey, if g of x is at arctan of x, I know all of you can write g prime of x without me having to remind you what it is. Go ahead and do it. There's no sarcasm. None. U prime over 1 plus u squared. Right? U prime over 1 plus u squared. What's our u here? X. Alec, what'd you get?
1 over 1 plus x squared.
Very good. And how did you get that?
U prime over 1 plus u squared.
And what was our u in this case?
X.
Okay. Yeah, good job. So okay, so now does this look like something you can do? Yeah. So let's go write that. Go write that little powered series for me. All good? Okay. And then, do I really like it like that? I like to try to get my x minus c, right, with the power. So what do you think we probably want to do? Can you rewrite this one more step? How we were practicing when we were integrating and differentiating? Remember how we pulled out the coefficient part? No, because you're all looking at me like, what the heck is she talking about? Okay, so it's very similar. And the other day, we were doing this guy. Remember that guy in your notes? And before we could integrate or differentiate, we had to separate things. Same concept. Because eventually, I am hoping to not have the power series for the derivative. I'm trying to get the power series for g, which means I'm going to have to do what with this power series? Antiderive. But I can't take the antiderivative when I still have an a sub n part going on in there. You know what I'm talking about now? What needs to be brought out? The negative 1 to the n. Okay, so we want to rewrite this. So basically we're thinking that this is a negative 1 times an x squared to the n. So we want to rewrite that as negative 1 to the n times x to the 2n. So we take out that coefficient. And I really don't need that a of 1 there. Now I think you guys could all find the derivative, which is the power series for arctan. Go. we did yesterday. Coefficient goes along for the ride. Woo! And take the antiderivative of x to the 2n, which would be x to the 2n plus 1 over 2n plus 1. Good. Good was that. Good job. Plus C. For the ease of some complicatedness for you guys, your C is always going to go to 0, okay? Just trust me on that, and we could have a whole nother class on that, but we're not going to take that. Okay? Okay. So that's how you do arctan. Isn't that cool? Yeah, so you find the derivative, use that derivative for the geometric sum already to go into a geometric power series, and then you take the antiderivative of the geometric power series to get to the arctan power series. So cool! Yeah! Okay, so we're going to do an AP one here. And let's look at this. Where are we centered? Let's just see what we know about this, just looking at f of x. Centered at -1. So it's x minus c. Okay, so we're centered at -1. Is this a geometric? Right here, is this a geometric? So we said we're centered at -1. And I could rewrite that as what? Okay, so we see that it's a geometric. So we could see that kind of going on. Just my thoughts when I first look at this are to think that. And I don't even know what the questions are asking me yet. But just looking it up, those are just my thoughts. Anybody else have another thought? Everybody say, well, gosh, those ones cancel. That? Now you do? Okay. So again, haven't looked at the questions, just my initial thoughts. So now let's go look at the questions. A says, find the interval of convergence of the power series for f and justify your answer. Okay. We're good at that. How many of you said I want to use the ratio test? Is that what test you want to use? It is. Okay. So a lot of us would do the ratio test just because that's normally what we do. And when we test our endpoints and we still get full credit. Okay? That's completely fine. But I'm going to do my shortcut way, which is from what we just learned. This is what type of series? Geometric. So instead of doing the ratio test, I'm going to use my geometric test on the original. Okay? And you would still get full points, and I bet half of you will still do it on the test. Okay? So no worries. But it says, find the interval of convergence. So this is a geometric power series. Okay? So if it's a geometric power series, my condition so this converges when the absolute value of r is less than 1. And what is my r in this case? X plus 1. Could you tell me your radius of convergence now? Since we have x minus c, it is 1. But now it wants the interval of convergence. So go solve for the interval. And we're done. There's no endpoints to be inconclusive on the geometric. So that's why I say if I can use my geometric, I'm going to. But ratio test would have worked just fine. You want to see how the ratio test would have worked out? Just so you can kind of compare it. It's not that long. Would you like me to do it really quick so you see? Yeah? Okay. So I would take the limit as n goes to infinity of the absolute value of x plus 1 times x plus 1 to the n, because it's n plus 1, over x plus 1 to the n, which gives me the absolute value of x plus 1. So that converges when x plus 1 is less than 1. So that's when x is less than 0 is less than negative 2. But on the ratio, we don't know those 2 points. That's when it becomes more extensive. So now I have to go plug those in. So when x is 0, this guy becomes 1 to the n. And what does that do? Diverges by geometric series. Okay? When x is negative 2, this guy becomes negative 1 to the n, which does what? Diverges by geometric series. So my final answer is this. Not that much more work, and you could have gotten the exact same points. But the shortcut is, if you know it's geometric, then awesome, because you don't have to go do all of that work. Okay? Alright. Because you have to do n plus 1, a sub n plus 1 over a sub n. So n plus 1. Okay. Alright, so A we could have done either way. Let's go on to B. And I'm just going to erase this so I can see. Okay, B. The power series above is the Taylor series for f about x equals negative 1. Find the sum of the series for f. I've already done that. Where did I already do that? We already found the sum. Go ahead. You guys can do perfect now. Knock at your table if you're like, what did she just tell me? Oh, talk it. Oh. Okay, go to your work, Chris. We'll look at that later. Tell me that in a little bit.
Calc off, yeah. AP calc off, yeah. Don't let go. Oh, jeez.
Good. Okay, C. Okay, so C says, let G be this function. So G of x is the integral from negative 1 to x of f of t. What would f of t be here? I found f. What would f of t be? What's f? What's f of x? Yeah, negative 1 to over s. We just found this for f, right? So here, that would be negative 1 over t dt. Find the value of g of negative 1 half. So they're asking me to find g of negative 1 half, which would what? Be the integral from negative 1 to negative 1 half of negative 1 over t dt. If it exists, or explain why it cannot be determined. Well, the only thing we can't have going on down here is what? 0. And I mean, I'd have to do a limit, but do I even have to worry about that? So can we find this? Okay, let's go do it. Go. So you should either get it's negative ln of a half or ln of 2. If you simplify it. You guys know how I would get that ln of 2. The ln rule with the power. So you can bring up negative 1. Either way, I don't care. You don't have to read this. Everybody good on part C? Maybe one more time for that. Okay, so let's go to part D. Let h be the function defined by h of x equals f of x squared minus 1. Pause. Can you all go write what h is now? This is a very basic function composition. I don't care how much you want to reduce it. There we go. Yes? Find the first 3 non-zero terms and the general term of the Taylor series for h about x equals 0, and find the value of h of 1 half. Well, could I find h of 1 half pretty easy first?
Yeah.
Let's do that, and then we'll go do the rest. Is that all right? Guys get 4/3. And on the AP test, should you stop there? Yes. Don't try to reduce on that AP test, okay? Everything with numbers and operations, you're good. All right. So then let's continue. It also wanted me to find the first 3 non-zero terms of the general term. So can I write this guy as a series? make it pretty easy to write the first few terms. What's my A? 1. What's my R? X squared. So that's going to equal
1.
And how many? Just 3? We've already got our general term. It's always the same thing as that. So that's x to the 2n. There we go. Did anybody see a different way that we could have done this right here? To me, this was just a pretty basic way of doing it. Did anybody say, well, that's f. Could I have found f of x squared minus 1? Just by function composition there. So that would have been 1 plus x squared minus 1 plus 1. X squared, which is what we had, plus x squared minus 1 plus 1 squared, which would have been x to the 4th. I mean, we could have done this, yes? With the whole general equation as well. There's always going to be a few different ways that you can get to the answer on this. So that would have been an AP free response question on a previous test. What do you think? If you've done it? Okay. So we are going to go back and do some more practice. Yeah. 8.8. You want to take a 30-second time out? Zach, what do you want to do? Okay. Now I think you gotta like say who wants some. They were just on the floor. I don't think Chris minds. I've seen him mind it. Peyton doesn't mind. Anybody else? That was an easy little solution. Anybody else want one that is just the floor? Shannon wants one. It was like a, no more than 5 seconds.
5 second rule. It's like the second rule though.
Alright, there we go. Okay, let's do this one and then let's go back and then we'll go forward. That way we don't do a long free response. We can have a shorter multiple choice. Okay? I know, kind of all over the place. Alright, so what is the radius of convergence of this series? Go. Is it geometric? No. So it's not geometric, so we're going to go ahead and do, the ratio test. Alright, go ahead. But it only wants the radius. We're going to have to do endpoints anyway. Yeah, I'm just kind of flipping-flopping this. with your limit. You want to check your limit. So I got x, the quantity of x minus 4 squared over 3 for my limit. So this is going to converge when this guy is less than 1. And again, our goal is to get it into this to find that radius. Yes? Yes. Okay, keep going. And how many of you guys got B? Be a good distractor? It's a good distractor because what did they not do if they chose B? They didn't do the square root. Okay, because you don't want the x minus c squared, you just want to get it to x minus c. So what's my answer? C! Alright. Thank you, Zach. Go ahead, put your paper tissue back. Yeah.
I got it, Zach.
Okay. So, alright, let's go back to the previous one now that we're good. Kind of got a basic one down. Or no, let's go ahead and do this. Alright, let's go ahead and do this next one. Trying to see if you understand some concepts here. That's why they gave you a spin so general. Anybody have any ideas? What's something you can tell me about this? I'll tell me at least one big thing about this series. Okay, but before you even look at that, just looking at the series, there's one thing you should all be able to tell me by now. C equals 3. Thank you, Cameron. Okay, we are centered at 3. So I'm going to just kind of make my little visual. Okay, I know I am centered at 3. Remember how we did that visual when we were making these? And if I'm centered at 3, and it told me it converges at 5, then minimally I have a radius of at least 2. Maybe it went out more, I don't know. But minimally I have a radius of at least 2. So I could also do what then? Do the opposite. Now, that would have been what? 2 and 1. Do I know that it converges at 1? No, but I know it's either open or closed. We don't know what happens there at 1. We can't guarantee it because endpoints can behave differently. But which one can I guarantee that is within that radius of convergence? 2. Okay, so that one is D. Okay? 100. Okay, Austin only. Where's this one? Down here. 0. Okay? Alright, this one right here was from a free response, but it was only part A. And this was worth, I think, 5 out of the 9 points. So if you get something that's already saying, find the interval of convergence, and that is all, and it's worth 5 points, you are like, thank you! Because you're going to see some that are pretty challenging and hard, and you're kind of like, what are they asking me? Okay, so this is more just a routine, and you have got to bank these points. This is an easy question here, comparatively, okay? The points you have to get. Go do it. I'm not saying it's an easy question. I'm saying comparatively, it is an easy question. Bless you. Okay. Little coefficient over coefficient because they're the same degree. See if you got that for your limit. I did. Keep moving on. So I know that when this guy's less than 1, it's going to convert by the ratio test. But I don't just have my x minus 0. I have an x squared. So I know I would have to take square root of 1. Well, that's easy enough because that's still just 1. Okay. But this was ratio tests, and points here are inclusive. Alternating series. So I got it to converge at 1 by the alternating series test. Because 1 to that 2n plus 1 just goes to 1. So we're just plugging in 1 for the x's, not the n's. Okay, so again, we're only plugging in the x to equal 1. The n's alone. That's what that one is again. Same thing, right? Just alternating series again. The terms are opposite. There we go. Questions on this one? Pretty straightforward. Okay, so there's nothing tricky. Nothing really to think of, like a ton about. It's just a process on this one. So we've got to get the process points. Okay, we're going to do one more problem, and that's this free response. This is the last one we're going to do together. Okay, so this could be F term by term, or F as a power series. Term by term. Okay, and again, we're going to think about what we did yesterday. So on part A, it says find the first 3 non-zero terms and the general terms for the Maclaurin series for f prime. So if they're term by term, what's easier to do for the f prime? Take the derivative of each one, term by term. Go. Okay, you should be like less than 30 seconds. I took the derivative, just the power rule of the first three, and then I took the derivative. This was already separated out for us, so that was nice of them. Okay, they didn't keep that negative inside where I have to separate it out. So we can just do the power rule there too. Good? Any questions on A? So then B, I had to think for a second. Because I was like, what are they doing here? Like, it took me a little bit. And I was like, oh! So look over it, see if you can see what are they doing on B. And they're telling you to use what you know for A. So look about what you just got for A and see if you can figure out what they're doing in B. Does anybody see it? Kayla? No? They're what?
They plug in 1/2.
They plugged in 1/2. Okay? They plugged in 1/2 for X. And that's a tricky one, and if you don't get it, you can move on to C, okay? So if you're looking at B for a while and you're like, what are they doing? Move on to C, because you don't need B for it, okay? How did you see that, Jackson? So do you see that they have this -3 in the square, right? So here I could see that what was squared was 1/2. Here I have a 6 and a 5th. So what was raised to the 5th? 1/2. Okay? So the tricky part was that they did a fraction. I'm sure if they would have just done, everybody would have said, oh, they plugged in 2. Okay? Like that was a lot easier to see, but this one was tougher because they made it into a fraction. Okay, so I can see they plugged in, which basically means that they were finding what? F prime of 1/2. How can I find F prime of 1/2? Look at the question. Oh, the whole question. Sometimes you got to go back up to the beginning. Find F prime of f of x and plug in 1/2. What's f of x? Yeah, 1/1 plus x to the 3rd. So find the derivative and plug in 1/2. How many of you guys are doing the quotient rule? How many of you guys rewrote it and are doing a chain rule? Okay. Either way. B high minus high, low, all over low, low. And you don't have to simplify that. But if you did, this is what you should get out. And I would go ahead and box it, and then just for now, practice your fraction rules. some kind of fun speech over in the other classroom earlier. Yeah. You acted like a high school girl. Well, that should have been fairly easy.
Ooh, dang.
Okay, so we do low, D high, and the top is 0. Minus high, D low, all over low, low. Okay. Yeah, derivative of 1 is 0. What's the derivative of pi? 0. What's the derivative of e? 0. What's the derivative of pi squared? 0. Okay. Okay, so now let's go on to C. C says, find the first 4 non-zero terms in the general term for this guy. So the integral from 0 to x of f of t dt is going to equal, and remember, like if we're integrating or deriving and we're given, here I'll just do that, we're given term by term, it's easier to go, what? Term by term. But they're plugging in what instead of x's? They're plugging these guys to be, whoa. They're plugging these guys to be t's. So let's go ahead and go term by term. Antiderivative. Okay. Antiderivative of 1 is x. Well, but we're doing t. Sorry. Yeah, because it's in the t's. So t minus 2 to the 4th over 4 plus t, t to the 7th over 7, minus t to the 10th over 2 plus plus negative 1 to the n t to the 3n plus 1 over 3n plus 1, and we are about plus and we are evaluating that from 0 to x. So let's plug in my x. Minus, plug in my 0. Oh, what do they all go to? 0. Right? So we're done. How many terms did I have to do? 4? Okay. Okay, so last part, question D. Is everybody okay so far with C? Okay, so question D. Use the first 3 non-zero terms of the infinite series in part C to approximate the integral from 0 to 1/2 of f of t dt. So I only want to do the first 3 terms now here in D. So what am I plugging in for x? 1/2. Alright, so that was pretty easy. Do I need to simplify? No, I'm not even going to bother right now. I don't want to have to do 2 to the 7th. 2 to the 5th is 32, 64, 128. 128 times. Anyway, okay. So there's D. What are the properties of the series that guarantee that this approximation is within 1/10,000 of the exact value of the integral? When you see that within 1/10,000, what's popping into your brain nowadays? The alternating series what? Error bound. Okay, awesome. So I have that error popping into me, and I can see that this is an alternating series. So I'm thinking the alternating series error bound. And in order to apply this, what do I have to have? Decreasing, and the limit is 0. Okay, so it has to be a convergent series, a convergent alternating series. So are these terms decreasing to 0?
Yes.
Check. Okay, so the terms are decreasing to 0. So we have met that condition. So since I've met that condition, what can I say was the alternating series error bound? That the actual, what's the actual in this case? Well, look at what's going on in context here. The actual is the 0 to 1/2 of f of t dt minus the approximation with the first 3 terms is less than or equal to the what? The next term evaluated at what here? 1/2. And guess what that is? That is less than, yeah. Woo! Guys, we have done a lot of AP practice in here. You should feel really good. Okay, that you were able to hang in there. Yes. Oh, okay. Really, really good question. I'm so glad you brought this up. So he says, hey, that's actually a negative, right? That's such a good question. So he says, why am I not putting a negative here? Yeah, because I'm talking about the error of the absolute value. So the absolute value here makes that go to a positive. And in all actuality, Cameron, if you want to put absolute values, you can, just like we do with the Lagrange. Okay? But like when we're doing that these terms decrease to 0, we're saying that the terms without the whole alternating part decrease to 0. So we're kind of looking at the terms without the whole alternating part when we go here. Does that help a little? Okay. Any more questions? So glad you brought that up, though. Good job. Okay, you get the rest of this class so you can work on your homework. You know.